Swayam Prabha. Digital India. Educated India.
In this course of Swayam Prabha, that is the mechanics of bodies, we will be discussing on the basic laws of physics to begin with, and then using those primary laws we will be starting to solve some very interesting problems using the tools and techniques of calculus of variations. So without wasting much time, let us start our discussion in this lecture, starting from the very basics which will be needed to develop our foundation. Okay, so again, so this course is on mechanics of bodies, and to begin with, in today's module, we will start with the basics, right? So for people who are not familiar with some some calculus ideas, we are going to recap some of those ideas which will be used later on in our further lectures. So basics. So the first course, crash course on the basics will be on the vector calculus. So we just begin with the very basic results in vector calculus. So to begin with, let us start with the absolute basic as to what is a vector. So people who are not familiar with what are vectors. So vectors are an abstract quantity. They are an abstract quantity characterized by both magnitude and direction. Characterized by magnitude and direction. So just to give a quick example, we have, suppose we have a particle which moves between 2 points A and B, and maybe it is taking some paths going from A and B, and we say that the particle has displaced from A to B, which is the straight line, the displacement. So we are talking about an example of a vector. So one example is the displacement vector. So the displacement of the particle from A to B, whatever path it has taken, doesn't matter, is so the displacement is the straight line joining A and B, right? And some other vectors, we call this displacement vector, we denote this displacement vector as A to B with an arrow. So this is our future notation, right? So starting point and the ending point and an arrow on top. Okay, so some of the other examples of vectors could be force. Well, of course, there are lots and lots of different types of vectors. We'll be only giving examples with those vectors which will be useful in this particular course. So one example is force. Another example could be electric field. We will look at all these different vectors in various examples that we will be discussing in subsequent modules. And then we also have magnetic field and so on, right? So once we have we have introduced vectors, let us quickly list some of the operations of vectors, some of the properties of vectors. So operations and properties. So linear. So first point of discussion is the set of linear operations on vectors. Okay, most of the readers will quickly familiarize themselves as these are very basic operations. For example, we talk about vector sum. Let's say two vectors A and B can either be summed with A plus B, or this is also equal to B plus A, right? And typically we associate vectors, we can even try to associate these operations, this sum and difference, for example, with this with the geometric method, that is that is using the so-called triangle law or the triangle inequality, or sorry, the triangle equality. So what I want to say is that suppose my vector A is denoted by this arrow, so where the length of the arrow is the magnitude of the vector and the direction of the arrow is the direction of the vector. And then we have, for example, the vector B given by this particular arrow. So then our net A plus B will be this third side completing the triangle. Okay. So then what we have is the so-called associative law. The associative law, for example, A plus B plus C is equal to A plus B plus C, right? We see that this is the associative law. And then we talk about the so-called inverse of a vector or the negative of a vector. Negative of a vector. So we talk about a vector. Let's say we have a vector A is being added with the negative of a vector B, and this is the same as the subtraction of A with B. Okay. And then we could also have the operation of so-called scalar multiplication. Scalar multiplication. So for example, if we have a scalar, and then if we multiply it with a vector, it means that now we have a new vector whose magnitude, the magnitude is equal to the scalar times the absolute value of the scalar times the magnitude of the original vector, and its direction is given by the original vector A, right? So just a few points of note here. So again we look at the scalar multiple of this vector, so lambda of A, so scalar multiple, okay. And just to give a brief idea as to what do we mean by this scalar operation. So suppose we have the direction of this scalar multiple lambda times A is the same as the vector A if same as A if lambda is positive and the direction is opposite or the correct word would be anti-parallel to A if your lambda is negative and we have that the direction is undefined. So I should say the entire word direction, okay. The direction is undefined if lambda is equal to 0, okay. So once we have these three cases, I think I should delete this last line. This is not going to be the case, okay. So we delete this last line, okay. So the direction could be defined in these three cases of the scalar multiple. Okay, so then we have some very trivial operations of these scalar multiples. For example, if we have two scalars lambda and mu, then we can say that lambda times mu of A is lambda mu times A. So what I want to convey with this simple operation is that you can first multiply with the first scalar and then multiply with the second scalar, or you can multiply the scalars together and then multiply it with the vector. Both are going to give you the same result, right? And then we have the second operation is the so-called distributive property. The distributive property scalar multiplication. So for example, lambda times two vectors, the sum of two vectors a plus b is lambda times a plus lambda times b. Okay. Just a quick again in the line of these recap of the basics, we can quickly look at one example. I think many of you will be familiar. These examples are mainly to familiarize some of the readers, some of the listeners on these topics. So, for example, suppose we want to perform this following operation. The problem says simplify. Simplify 3 times 2a minus 4b minus 2 times 2a minus b. Okay, so let me put arrows where there are vectors. Okay, so all these quantities 3, 2, 4, minus 4 and all these things are scalars, right? So we can quickly use all these two operations. Let me call this operation number, well, these are operation 1 and 2. So using 1 and 2, we can quickly add up and appropriately simplify and multiply. So we have 3 times 2 minus 4. So that is going to give you 2 times a, and 3 times minus 4 is minus 12, and plus 2 will be giving you minus 10b. So that is a quick answer to this problem. So these are just quick recaps. So again, another concept along the lines which are very important in vector calculus is the so-called the concept of unit vectors. Okay. So what is unit vector? Unit vector is a vector of magnitude 1, vector of magnitude 1, and hence the name unit vectors, and the direction of the vector being that of the original vector. So readers, listeners can quickly realize that unit vectors, let's say if we want to find the unit vectors corresponding to a vector A, we can quickly divide by the magnitude of A, right? We can see that the magnitude of this unit vector is, this vector is 1, and then of course the direction is that of the direction of A. The denominator doesn't have any direction. Okay, so then we talk about this. These are some very basic ideas in linear algebra. The first idea is that of the basis vectors, basis or the basis set. So let me start with this concept of basis set in 2 dimensions, that is basis set over a plane. So suppose we have 2 vectors A and B, which are coplanar. So what I mean by coplanar is that we have 2 vectors which are lying on the same plane. So let me say that this is, my first vector is A and the second vector is B, right? And so vectors which are coplanar with direction, well, this is important, with direction of B neither parallel nor anti-parallel to A. Okay, so B does not align with A, or it is not aligning opposite to A. So basically there is some angle between the 2 vectors, right? So now we have that if we have any vector V, so for any vector V in the 2-dimensional plane, I can always write V to be a linear combination of the 2 vectors A and B, right? So V is lambda times A plus mu times B. So which means I can represent any vector in the 2D plane as a linear combination of these 2 coplanar vectors A and B, which are not parallel or anti-parallel. So basically they are not linearly dependent on each other. And then we call these two vectors to be our basis set, right? Now, so these two vectors A and B could be anything, not necessarily unit vectors or orthogonal. Well, I have to introduce all these terms. So we have already introduced the term unit vectors. So these vectors could be anything, whether or not unit vector, it doesn't matter. But as long as they are neither parallel nor anti-parallel, they can serve as my basis set. So what do I mean by basis set? The set through which we can represent any vector in 2D with a suitable linear combination, right? So then similarly we can, let me call this as my concept A. Similarly we can talk about my basis set in 3D, right? So what do we have? So we can again start by saying that let us say we have set of 3 vectors A, B, C, and they are non-coplanar. So what do I mean by this is, so this word non-coplanar, as the name suggests, is they do not lie in a single plane. Because if one of the if these vectors are coplanar, then we can certainly represent the third vector in terms of the other two. Represent the third vector in terms of the other two using this relation. Let me call this as 1. Okay. So we need this condition to be that these 3 vectors to be non-coplanar. So then in that case, for any vector in 3D, we have the vector V is lambda times A plus mu times B plus gamma times C. So we can linearly represent the vectors V in terms of A, B and C, right? And then what we have is, so this is my basis set. Now from here we can introduce we can introduce one more concept, and using that concept we will introduce the so-called standard basis set, right? So the concept that I want to introduce is that of orthogonality of vectors. So what we have is, so suppose if we have, again we are introducing all these ideas geometrically. So as the name suggests, 2 vectors are orthogonal to each other. Let's say A and vector B are orthogonal to each other if the angle between them is 90 degrees, right? And we can quickly, so that is the case. And similarly, if we have a third vector C, so first we have to make sure that the C is non-coplanar, right? So they are vector C is not lying in the plane of A and B, and also the angle between B and C and A and B should be 90 degrees. And now we have a set of orthogonal, so we have an orthogonal basis A, B, C, such that the angle between any of these 2 vectors is 90 degrees and they are non-coplanar, right? And then from here we can also introduce a corresponding idea of orthonormality or orthonormal vectors, orthonormal basis, right? So what do I mean by this? On top of these vectors A, B, C being orthogonal, suppose we divide by their magnitude. So we have, let's say, vector A divided by the magnitude of A, vector B divided by the magnitude of B, and so on. And what I am going to get is the set of 3 unit vectors which are orthogonal and non-coplanar, and typically we call this orthonormal basis as my standard basis. standard basis in 3D, in 3 dimensions, standard basis in 3 dimensions. Typically we denote this this basis as my basis by I, j, k hat. Okay, you can say that my vector A has been reduced to I hat, B has been reduced to j hat, and C has been reduced to k hat. And I, j, k hat, they typically point along the 3 axes in 3 dimensions, and they are each of magnitude 1, right? So which means that if I were to represent any vector v in 3D, that is going to be lambda times I hat plus mu times j hat plus gamma times k hat. So now we have this orthonormal basis or the standard basis with which we can represent any vector in 3D. Okay, so then so I think in terms of the very basics, I think we are all set. We will now slowly start to define some basic physical quantities, and using that we are going to start with some more non-trivial results, more mathematical results, because this is overall a mathematics course, and we'll see how it goes. Okay, so what do we have? So to begin with, let us start with the basic definition of position vectors. Position vectors. Okay, so what we have is, so we are going to define our position vectors. So position vectors, we say that a vector is a position vector. It's a position vector of relative to some origin O of the standard basis or the coordinate basis, right? So what I just said is the following: a vector A is the position vector of a point, let's say a point A, okay, of a point A relative to the origin O. So once we are talking about origin and all these ideas, which means that we are talking with respect to some coordinate axis or some standard basis. You can call the standard basis the standard basis of I, j, k as my coordinate axis, and this coordinate axis has an origin O, and suppose we have a point A in 3D space, and this point A will have a position vector represented by an arrow drawn from O to A, and we call this position vector of point A to be the vector OA. Okay, so that's my position vector of the point A. Let us look at some very basic mathematical results which we can derive right away. So these are some interesting results, and also some of these are again some recap as well. So the first result is related to a point dividing. So let me not name this in the form of a theorem, but this is just a result. So point dividing a line in a given ratio. Okay. So what it says is, suppose we have a line, let's say a line is given by AB, right? So a line, and which means the moment we are talking about these points in 3D, it is going to have position vectors. Let's say position vectors OA and OB. Let me call this position vector OA to be vector A, and position vector OB to be vector B, right? So now, which means the position vector AB is going to be the vector B minus A, the final point minus the position vector of the final point minus the position vector of the initial point. So now the problem says is, suppose we have a point, let's say X. let me call this point with capital X, right? And now what I am trying to say is, so again, given this point, it will now have a position vector also. So this position vector of this line OX is going to be, say, small x, right? So what it says is, suppose this point X divides the line, it divides the line. Well, let me write this statement and then I can tell it in a bit more succinct way. So what it says is, suppose points A and B have position vectors A and B relative to O. Okay, so we find the position vector, we find the position vector of x that is of the point X, right? So we find the position vector of X. X is nothing but the line OX, right? Such that this point X divides AB in the ratio, in some ratio, right? So let's say in the ratio lambda is to mu. So what the problem says is, let us say that this point X is dividing the line AB in the ratio lambda to mu, and we need to find this position vector OX. So this is what we need to find. This is not known. The information that is given is the point X of this position vector X divides the line segment AB in the ratio lambda is to mu, right? So we see that, so what is given now is, so what is given is that the ratio AX over XB is lambda to mu, right? And we see that the point X is A plus, well, the point, this vector X, OX, right? So I should write like this. So I'm just using the triangle law here. So the vector OX is going to be OA plus AX, right? So this is going to be OA plus AX, right? So then, so my OX vector is my vector small x, and my OA vector is A, and my AX vector is, we can see that from this particular result, let me call this as 1, is going to be lambda divided by lambda plus mu times the vector AB, the full line, right? So this is using 1, right? And now we can see that my vector AB, so this is going to be A plus lambda divided by lambda plus mu times, my vector AB is nothing but B minus A. And from here we can simplify this result, and we are going to get that this is going to be mu A plus lambda B divided by lambda plus mu, right? So whenever we are given the position vectors of 2 points and we want to find the position vector of a point in between, we can quickly apply this result, that we need to, well, the position vector of the point in between will have this answer in the form of these ratios mu and lambda.